The traveling salesman problem asks the following question. Given a list of cities and the distances between each pair of cities, what is the shortest possible route that visits each city exactly once and returns to the origin city? It is an NP-hard problem in combinatorial optimization, important in operations research and theoretical computer science. TSP is a special case of the traveling purchaser problem and the vehicle routing problem. In the theory of computational complexity, the decision version of the TSP belongs to the class of NP-complete problems. Thus, it is possible that the worst-case running time for any algorithm for the TSP increases superpolynomially with the number of cities. The problem was first formulated in 1930 and is one of the most intensively studied problems in optimization. It is used as a benchmark for many optimization methods. Even though the problem is computationally difficult, a large number of heuristics and exact methods are known, so that some instances with tens of thousands of cities can be solved completely, and even problems with millions of cities can be approximated within a small fraction of 1%. The TSP has several applications even in its purest formulation, such as planning, logistics, and the manufacture of microchips. Slightly modified, it appears as a sub-problem in many areas, such as DNA sequencing. In these applications, the concept city represents, for example, customers, soldering points, or DNA fragments, and the concept distance represents traveling times or cost, or a similarity measure between DNA fragments. The TSP also appears in astronomy, as astronomers observing many sources will want to minimize the time spent slewing the telescope between the sources. In many applications, additional constraints such as limited resources or time windows may be imposed. History. The origins of the traveling salesman problem are unclear. A handbook for traveling salesmen from 1832 mentions the problem and includes example tours through Germany and Switzerland, but contains no mathematical treatment. The traveling salesman problem was mathematically formulated in the 1800s by the Irish mathematician W.R. Hamilton and by the British mathematician Thomas Kirkman. Hamilton's Icosian game was a recreational puzzle based on finding a Hamiltonian cycle. The general form of the TSP appears to have been first studied by mathematicians during the 1930s in Vienna and at Harvard, notably by Carl Menger, who defines the problem, considers the obvious brute force algorithm, and observes the non-optimality of the nearest neighbor heuristic. We denote by messenger problem the task to find, for finitely many points whose pairwise distances are known, the shortest route connecting the points. Of course, this problem is solvable by finitely many trials. Rules which would push the number of trials below the number of permutations of the given points are not known. The rule that one first should go from the starting point to the closest point, then to the point closest to this, etc., in general does not yield the shortest route. It was first considered mathematically in the 1930s by Merrill Flood, who was looking to solve a school bus routing problem. Hassler Whitney at Princeton University introduced the name traveling salesman problem soon after. In the 1950s and 1960s, the problem became increasingly popular in scientific circles in Europe and the USA after the Rand Corporation in Santa Monica offered prizes for steps in solving the problem. Notable contributions were made by George Dantzig, Delbert Ray Fulkerson and Selma M. Johnson from the Rand Corporation, who expressed the problem as an integer linear program and developed the cutting plane method for its solution. They wrote what is considered the seminal paper on the subject, in which with these new methods they solved an instance with 49 cities to optimality, by constructing a tour and proving that no other tour could be shorter. Dantzig, Fulkerson and Johnson, however, speculated that given a near-optimal solution we may be able to find optimality or prove optimality by adding a small amount of extra inequalities. They used this idea to solve their initial 49-city problem using a string model. They found they only needed 26 cuts to come to a solution for their 49-city problem. While this paper did not give an algorithmic approach to TSP problems, the ideas that lay within it were indispensable to later creating exact solution methods for the TSP, though it would take 15 years to find an algorithmic approach in creating these cuts, as well as cutting plane methods. Danzig, Fulkerson and Johnson used branch and bound algorithms perhaps for the first time. In the following decades, the problem was studied by many researchers from mathematics, computer science, chemistry, physics, and other sciences. In the 1960s, however, a new approach was created. Instead of finding optimal solutions, people tried to instead find the worst solutions and in doing so, created lower bounds for the problem. These may then be used with branch and bound approaches. One method of doing this was to create the minimum spanning tree of the graph and then multiply the cost of this by 2. Christofides made a big advance in this approach of giving an approach for which we know the worst-case scenario. His algorithm, given in 1976, at worst is 1.5 times longer than the optimal solution. As the algorithm was so simple and quick, many hoped it would give way to a near-optimal solution method. However, until 2011, when it was beaten by less than 0.1%, this remained the method with the best worst-case scenario. Richard M. Kopp showed in 1972 that the Hamiltonian cycle problem was NP-complete, which implies the NP hardness of TSP. This supplied a mathematical explanation for the apparent computational difficulty of finding optimal TORs. Great progress was made in the late 1970s and 1980, when Grochel, Padberg, Rinaldi and others managed to exactly solve instances with up to 2,392 cities, using cutting planes and branch and bound. In the 1990s, Applegate, Bixby, Schvartal, and Cook developed the program Concord that has been used in many recent record solutions. Gerhard Reinelt published the TSP-LIB in 1991, a collection of benchmark instances of varying difficulty, which has been used by many research groups for comparing results. In 2006, Cook and others computed an optimal TOR through an 85,900 city instance given by a microchip layout problem, currently the largest solved TSP-LIB instance. For many other instances with millions of cities, solutions can be found that are guaranteed to be within 2 to 3% of an optimal TOR. The problem is sometimes, especially in newer publications, referred to as traveling salesperson problem. Description: as a graph problem, TSP can be modeled as an undirected weighted graph, such that cities are the graph's vertices, paths are the graph's edges, and a path's distance is the edge's length. It is a minimization problem starting and finishing at a specified vertex after having visited each other vertex exactly once. Often, the model is a complete graph. If no path exists between two cities, adding an arbitrarily long edge will complete the graph without affecting the optimal TOR. Asymmetric and symmetric: in the symmetric TSP, the distance between two cities is the same in each opposite direction, forming an undirected graph. This symmetry halves the number of possible solutions. In the asymmetric TSP, paths may not exist in both directions or the distances might be different, forming a directed graph. Traffic collisions, one-way streets, and airfares for cities with different departure and arrival fees are examples of how this symmetry could break down. Related problems: an equivalent formulation in terms of graph theory is: given the complete weighted graph, find a Hamiltonian cycle with the least weight. The requirement of returning to the starting city does not change the computational complexity of the problem. See Hamiltonian path problem. Another related problem is the bottleneck traveling salesman problem. Find a Hamiltonian cycle in a weighted graph with the minimal weight of the weightiest edge. The problem is of considerable practical importance, apart from evident transportation and logistics areas. A classic example is in printed circuit manufacturing. Scheduling of a route of the drill machine to drill holes in a PCB. In robotic machining or drilling applications, the cities are parts to machine or holes to drill, and the cost of travel includes time for retooling the robot. The generalized traveling salesman problem, also known as the traveling politician problem, deals with states that have cities, and the salesman has to visit exactly one city from each state. One application is encountered in ordering a solution to the cutting stock problem in order to minimize knife changes. Another is concerned with drilling in semiconductor manufacturing, CEG, U.S. Patent 7,054,798. Surprisingly, Bezard and Modores demonstrated that the generalized traveling salesman problem can be transformed into a standard traveling salesman problem with the same number of cities, but a modified distance matrix. The sequential ordering problem deals with the problem of visiting a set of cities where precedence relations between the cities exist. The traveling purchaser problem deals with a purchaser who is charged with purchasing a set of products. He can purchase these products in several cities, but at different prices, and not all cities offer the same products. The objective is to find a route between a subset of the cities, which minimizes total cost and which enables the purchase of all required products. Integer linear programming formulation. TSP can be formulated as an integer linear program. Label the cities with the numbers chapter 0, n and define, for I equals 0, n, let be a dummy variable, and finally take to be the distance from city I to city j. Then TSP can be written as the following integer linear programming problem. The first set of equalities requires that each city be arrived at from exactly one other city, and the second set of equalities requires that from each city there is a departure to exactly one other city. The last constraints enforce that there is only a single tour covering all cities, and not two or more disjointed tours that only collectively cover all cities. To prove this, it is shown below that every feasible solution contains only one closed sequence of cities, and that for every single tour covering all cities, there are values for the dummy variables that satisfy the constraints. To prove that every feasible solution contains only one closed sequence of cities, it suffices to show that every subtour in a feasible solution passes through city 0. For if we sum all the inequalities corresponding to for any subtour of k steps not passing through city 0, we obtain, which is a contradiction. It now must be shown that for every single tour covering all cities, there are values for the dummy variables that satisfy the constraints. Without loss of generality, define the tour as originating at city 0. Choose if city I is visited in step t. Then since can be no greater than n and can be no less than 1, hence the constraints are satisfied whenever for we have satisfying the constraint.